is the electric flux through the surface. Now, I mentioned that it's parallel to the XY plane because I didn't want to have to get into, well, I gave more information than I had to. I'm not contradicting myself, but I didn't want you to have to worry about the three-dimensional problem. We have this electric field that's coming in at an angle 30 degrees from the horizontal, with respect to the horizontal. In fact, I should write 30 degrees with respect to the X and Z plane. Because the answer doesn't change if I reorient it, so that's why horizontal is a vague term there. All right, so what I need to do is figure out, well, first what my two vectors are. I've got this electric field coming in like this, and that's 30 degrees. And then I have my area vector, which is like that, going with Olivia's first response of positive j hat. And I need to figure out the angle between them. So I've got area going up like this, so I put them tail to tail. And I need to figure out that angle. What is that angle? I'm assuming the stunned silence is just you're just so in awe of physics that it's rendering you speechless.
120 degrees?
Okay, yes. Because all I've done is just extend it that way. I know this angle here is 30 degrees. So if I add 90 to it, I get to 120. And so the electric flux is just the magnitude of my electric field, which I did not give. I get 2 newtons per coulomb. It's the magnitude of my electric field times my magnitude of my area vector, which was 24, times the cosine of that angle. And we end up with 24 Newton meter squared per coulomb. Negative. Now, some students, I've given problems like this before on tests. Some students see the angle and immediately just plug the angle in there, 30 degrees. You'll be off because that's why I picked that one. Does that satisfy your need for the moment? Or do you have a follow-up question? Or anyone else have a follow-up question?
Now, if it was, instead of going in this direction, if it was going in the other direction, would you use the 30-degree angle there, or is it still the same process?
Still the same process.
Okay.
If I had gone the other direction, then ultimately, yeah, that's 30 degrees. So if I hadn't gone the other direction, then I'd use 60 degrees as the angle I plug into there, and then get a positive answer.
Okay, I see.
Yeah, the more I have trouble coming up with a problem on the spur of the moment, there's some other interpretations of the way I've worded this that could show up, because, yeah, because you could have, from this interpretation, had it going in that direction as opposed to that direction. And my questions just get longer and longer as I think of all those things I don't want people to be answering.
But electric flux doesn't have a direction.
Correct, it is a scalar. Dot products are scalar products. And for those of you who are cross product fans, don't worry, when we get to magnetism, cross products will rear their beautiful head. And for those who are more dot product fans, then cross products will rear their ugly head. Questions on anything from, well, pretty much anything related to physics? All right, let's talk about current. This is basically chapters 18 and 19 deal with electrostatics. We're not really dealing with moving charge other than charge moves over a surface and distributes in particular ways. Now we're dealing specifically with, we have charge moving. And if charge is moving, we have what is known as current. Again, the water analogy applies here, that since that was basically the mental model that was being used as the vocabulary is coming up, as they're coming up with the vocabulary. So current, the symbol for current is I, or I. It's a capital I based, the general rule of thumb is if you're dealing with direct current, then you use the capital letter and then the smaller letter for alternating current. That's the general rule of thumb. Direct current, all the charges tend to go in the exact same direction. Alternating current, the charges are forced one direction, then they're forced back the other way, then forced back and forth. Alternating current we will not deal with until we've gotten some more magnetism out of under our belts. It's a later chapter concept. Direct current, though, is what we're dealing with in chapter 20. So, like AC and DC. I had a good friend in college. Her name was Andrea Clarice Smith, AC. Her brother's name was David Clark Smith, DC. Their dad was an electrical engineer. She insists that it was not a coincidence. I was more surprised that their mom let him do it. All right, so if there's a current, that means we have a moving charge. So there exists moving charge. Since there's moving charge, we can define current in terms of moving charge. And it's generally written delta Q over delta T. Now, typically delta means change, like it does delta T is the change in time. This change in current is a little bit more of a nebulous wording there, because if I have a wire here hooked to a battery, I'm going to have current flowing through the wire. Current flows from the high potential to the low potential. So I have current flowing through the wire. And if I look at the number of charges in this section while the current is flowing, I can come up with a number. I look a moment later, I have the exact same number. The amount of charge in this area is pretty much stays the same. But I have current flowing through it, and this delta Q is a reference to the charge that's flowing through. So delta Q, not really change in charge in an area, this is amount of charge that flows. So let's just do a quick plug and chug. I've got a little section of wire right here, and I have 5 coulombs. Every 5 coulombs pass that point every 15 seconds. What is the current? Well, how much charge passes through? Wow, unison would have been really cool there. 5 coulombs, how much time?
15 seconds.
Do the fancy math, you get 0.33 repeating. Units?
Coulombs per second.
Now for some reason, you come up with a Newton meter squared per coulomb, they're fine with that, but coulombs per second is too much to say, so there's a one-word answer for this, 0.33 amperes. So that is the spelling of the unit. The man it's named after, I think that's the spelling. I think I have the accent mark right. Yeah. Again, my French pronunciation is horrible, but something along those lines. All right, so let's make it seem more complicated. I have my section of wire right here, and passing this point right here, I have 3 electrons going to the right. Oh, actually, let's make it 3 protons to start with. Then I'll mess with your heads. I have 3 protons going to the right. Every 10 seconds. What is the current now? All right, so what is the charge? I'll get the denominator for you. 10 seconds. All right, so what's the charge that's flowing?
It's going to be the charge of a proton times 3.
Yeah. And what is the charge of a proton?
1.6 times 10 to the negative 19 coulombs.
Negative 19.
Yeah.
1.6, did you throw another number in there?
No.
Okay. I didn't know if I heard something else. All right, and so, yeah, the biggest mistake I see students make when I give this type of problem is they just go with, oh, the charge is 3. That's chemistry talking there. Physics, we've got to actually multiply by the charge in coulombs. So let's see, 3 times 1.6 is 4.8 divided by 10. So we end up with 4.8 times 10 to the negative 20th. Coulomb. Sorry. Amperes. We definitely don't have anything that would measure a charge that small. Presumably somebody does. Not us. That'd probably be multi-million dollar equipment to be able to detect charge that current that small. All right, questions to here before I make it look more complicated. All right, let's make it look more complicated. I got a section of wire here, right, passing through there. I have 3 electrons moving to the right. what is my current now? So we would just take a gut shot at it?
Is it still every 10 seconds?
Oh, yeah, every 10 seconds. Yes, thank you.
It'll be the same thing, it's just negative in front.
Is it the same thing?
Yeah, you just have to add a negative in front of the.
So you're saying negative 4.8 times 10 to the negative 20th amperes?
Yes.
That would make sense, wouldn't it? What does the negative mean?
Yeah,
Pardon?
it's like no charge, right?
No, it's not a no charge thing.
Oh.
Gina, say it.
It's going the opposite direction.
What's going that way?
The answer is saying it's going that way, but it's not.
Yeah, the current is what I was shooting for there. So in this particular case, the current is flowing this way. In this particular case, the current is flowing this way. So it's either negative 4.8 times 10 to the negative 20th amperes that direction, or 4.8 times 10 to the negative 20th amperes that way. These are both correct answers.
And then, for our answers, do we have to indicate like what direction?
Sometimes.
Okay.
It depends on the way the question's worded. I will tell you on the last question of test 1B, yes, direction matters. You will need to say what the direction is. If you look at the old test for test 1B, you will see what the last question will be, other than the numbers will change. But. All right, so when they were trying to figure out current, I have a high potential and a low potential. So when I'm doing a battery, see, I've done the battery symbol in here before, right? Okay, I got a nod. So we've got the high side and the low side. They figured Franklin was coming up with this stuff, and he said, I got high potential, low potential, current flows from high to low. So he established that current flows this way. And then I think as mentioned before, later realized that, well, he didn't. It was later realized by physicists that what's really flowing is electrons flowing the other way. But current is still the direction of, in theory, a positive charge flow, or opposite a negative charge flow. By the time they realized what was going on, they decided they're not changing the convention. So some textbooks will sometimes make a reference to electron current. The electron current being the direction that would be positive direction the electrons flow. I tend not to use the term electron current just because I'm fine with just using current, and it's opposite the negative charge flow or the same direction as the positive charge flow. Now what's really going on when current flows is, if you think about a river, you look at a river and you see water flowing down, it looks all nice and neat, but if you actually got down to a more specific level, water doesn't flow in a straight line, especially at the banks. You hit a rock at the bank and the water has to go around it. Because that's going around it, it affects another water molecule, and affects another, I mean, so it's not really going straight. You get these eddy currents along the way too. Or near Niagara Falls, there's a whirlpool. So if I sort of expand the section of wire there, so sort of a zoom in on the wire, and let's say this is my high and low potential. Which way will my current flow? Right to left, or left? Will it flow left or right?
It's going to flow to the right.
Current will flow right. Which way will the electrons go?
To the left.
Yeah. So as the electrons are moving in here, they're going to hit things. you got a whole bunch of atoms in there. The electrons are going to get sort of distracted. So it'll hit and it'll bounce, and then it'll hit something else and bounce, and hit something else and bounce, and hit something else and bounce. So there's a general trend for the electron to move in a particular direction, but it's definitely not in a straight line. Actually, if you do get electrons start traveling in a straight line, we're dealing with superconductivity. That is not what we're talking about right now. We're talking about just normal everyday flow. So there's the speed of the electron as between hitting things, and then there is the actual practical speed of it, and that practical speed is known as the drift speed. Sometimes referred to as drift velocity. Yeah, I guess direction does matter there, so drift velocity. Oh, that does bring up, current is a scalar. And yet, there's a direction here. So why is it a scalar? Well, here's the justification for it being a scalar. I have current flowing out of here, and current's going to come to a junction. Some of the current's going to flow this way, some of the current's going to flow that way. If it were a vector, at that intersection, I have a current flowing in. If it is a vector, all my current is to the right, therefore the current leaving that junction also would have to be to the right. There's no vertical component here, so there can't be vertical component after the junction. It is a scalar because the current will split. The sum of these two, the sum of the magnitude of these two is equal to the sum of this, but the direction does not figure into this addition problem. So if that's 5 amperes, this might be 2 amperes and 3 amperes. But direction is not figured into that math. We are dealing with scalars, even though there are positive and negative directions. But the same is true with time. There's positive and negative time, but time is a scalar. All right, so we have this thing bouncing around. If I'm looking at